Hello students, welcome to another lesson on engineering thermodynamics. Today I will be discussing some problems related to regenerative power cycle. Consider a steam power plant operating on the ideal regenerative Rankine cycle with one open feed water heater. Steam enters the turbine at 15 megapascal and 600 degrees Celsius and is condensed in a condenser at a pressure of 10 kilopascal. Some steam leaves the turbine at a pressure of 1.2 megapascal and enters the open feed water heater. We are going to determine the different quantities A to I. So this problem is an ideal regenerative Rankine cycle, and we are given with one open feed water heater. It's given that we have 15 megapascal as our boiler pressure. We also are given with 10 kilopascal, the condenser pressure, and 1.2 megapascal, the pressure at the open feed water heater. So let us draw the equivalent schematic diagram as well as the TS diagram for this problem. So since this is a regenerative Rankine cycle, this is how we draw the schematic diagram for a regenerative Rankine cycle with one open feed water heater. So based on the problem, the steam enters the turbine at 15 megapascal and 600 degrees Celsius. Then, at the turbine, we extract a quantity of steam to the open feed water heater, which is operating at 1.2 megapascal. The remaining steam will expand to the condenser at a pressure of 10 kilopascal. Those remaining steam that condenses will be compressed to a higher pressure by a pump 1 so that it will reach the pressure of the open feed water heater. Then in the open feed water heater, this water will mix with the steam that we extracted in the turbine. They will mix and then it will exit at point 3 as a saturated liquid. So the pressure at point 3 is the same as the pressure at the open feed water heater, which is 1.2 megapascal. And in order for that feed water heater to reach the boiler, we need to compress it again using another pump to a pressure of the boiler at point 4. Now the cycle will be completed as you can see here in this schematic diagram. So based on this schematic diagram, we have 5 major components. First, we have the turbine that produces work. We have the condenser, which rejects heat. And we have the pump 1 and pump 2. The purpose is to compress the feed water and to increase its pressure. We also have the boiler, which is used to generate the steam. In addition to the components, we have the feed water heater. In this case, we have the open feed water heater. So take note that the operation of the open feed water heater it's like a mixing tank or a mixing chamber wherein the fluid that enters in the feed water will mix all together. And in order for them to mix, they have to be at the same pressure. That's why the pressure of the steam at point 6, the pressure of the steam entering at point 2 will have the same pressure so that they will mix. And they will also exit the feed water at the same pressure, which is at point 3. Also, another feature of the open feed water heater is that the steam leaves the heater as a saturated liquid. That's why at point 3, the steam is already the feed water is already a saturated liquid. Another thing that we need to note for the operation of open feed water heater is that it needs a pump at the exit so that it can handle the working fluid or the feed water leaving this. That's why we need the pump too. So that is why in this schematic diagram, we can see 3 operating pressure, which is 15 megapascal, 1.2 megapascal, and 10 kilopascal. We can also see here the quantity of steam that is being extracted from the turbine. At point 6, we extract Y quantity of steam. So this Y quantity is a fraction of the total steam that is passing through the boiler. Since we extract Y quantity, the remaining quantity that will be condensed will just be the total minus Y, or 1 minus Y. So this 1 minus Y will flow through the condenser, will flow through the pump 1, and will enter the open feed water heater. As you can see here, it will mix with this Y quantity so that when they mix at point 3, the result will be the total, or the 100% of the steam that passes through to the boiler. For the equivalent TS diagram of this schematic diagram, so we have here this TS diagram. So as you can see, it is divided into 3 operating pressure, the 15 megapascal, the highest one, which is also the boiler pressure. We also have the 1.2 megapascal, which is the pressure of the open feed water heater, and the 10 kilopascal, which is the pressure of the condenser. That's why we have 3 constant pressure lines, as you can see here. So at point 1, it leaves the condenser as a saturated liquid. Then it will be compressed to point 2, wherein it will become a compressed liquid at a pressure of the open feed water heater. Because it will not enter the open feed water heater if it will have a different pressure. That's why the pressure at point 2 will be the same pressure as that of the open feed water heater. That's why at point 2 and point 3 and point 6, they have the same pressure. So point 2, point 3, and point 6 have the same pressure. So as you can see here in the schematic diagram, they are the points that is connected to the open feed water heater. So at point 2, from point 2, it will enter the open feed water heater, where it will mix with the steam that is extracted from the turbine, which is point 6. So this point 6 is actually a hot steam. So it's a superheated, as you can see here in the diagram. So this point 6 will mix with point 2 at the open feed water heater, and the result will be a saturated liquid at point 3. That's why we have point 3 is a saturated liquid at the same pressure, which is 1.2 megapascal. So again, the purpose of the feed water heater is to heat the feed water. So it was able to accomplish that purpose by heating the feed water heater, which is originally at point 2, it now became point 3, which is a saturated liquid. Then from point 3, it will further be compressed and heated to point 4 by another pump so that it will reach the pressure of the boiler. That's why at point 4, the pressure here is the same as the pressure at point 5. And that is the boiler pressure of 15 megapascal. Then from point 4, the feed water will undergo boiling because of the heat generated by the steam generator in the boiler, where it will reach a superheated state at point 5. So as you can see here, from point 4, it will be heated to point 5, which is at 15 megapascal and 600 degrees Celsius. You should also take note that if you can observe, the purpose of the regenerative Rankine cycle is to basically increase the average temperature of the heat addition process. And as you can see here, we were able to achieve that by raising the temperature from point 2 to point 4, which is a big leap in terms of the average temperature of the heat addition process. So now at point 6, it is a superheated vapor at 15 megapascal and 600 degrees Celsius. It will now enter the turbine, where it will expand, but at point 6, it will be extracted, as you can see here in the diagram. And then the remaining steam will expand completely to 0.7 at the condenser pressure of 10 megapascal. So at the condenser, it will release or reject heat to the atmosphere, and it will go back to its saturated liquid state to complete the entire cycle. So basically, that's how we can draw the schematic diagram. And the TS diagram, if we have an open feed water heater. So now that we have the various points, points 1 to 7, we are now ready to get the different enthalpies at the various points in the cycle. So what we're going to do is we tabulate if you are using the software, and you can also use the steam table, whatever is more convenient to you. So we have points 1 to 7. So based on our schematic diagram, point 1 is a saturated liquid because it is where it leaves the condenser. Point 2 is a subcooled liquid based also in the TS diagram. Point 3 is saturated liquid because it is where it leaves the open feed water heater. So take note that every time that it leaves, it will be saturated liquid. Point 4 is a subcooled liquid. Point 5 is a superheated vapor because it is where it reached the maximum pressure and temperature. And then point 6 is a superheated vapor, and point 7 is a mixture. So based also in the TS diagram, point 1 and point 10 is a constant pressure line. That's why they have the same pressure. Also point 2, 3, and point 6 is a constant pressure line because they are connected to the same component, which is the open feed water heater at 1,200 kilopascal. Point 4 and 5 is the boiler pressure, which is 15,000 kilopascal. We're also given with the temperature at the inlet of the turbine, which is 600 degrees Celsius. Another important component that you need to understand here is the mass flow rate that is flowing through each of the components. Because unlike the previous cycles that we analyzed so far, in the regenerative Rankine cycle, the mass flow rate at the components will vary depending on which loop it belongs to. As you can see here, we actually have two loops. So these loops here representing the pump 2, boiler, and this part here of the turbine, and also another loop here for the condenser and the pump 1. So we need to determine the mass flow rate flowing through each of the components. So the best thing to do is to make the flow rate at the boiler as m. So that's why at 0.5 the flow rate is m. Same also with 0.4 because this is the same loop. So that's why at 4 the mass flow rate is still m. So 4 and 5 the mass flow rate will be considered m, or basically that's just the mass flow rate through the boiler. And then at 0.6 you can see that we extract y quantity. That's why at 0.6 the flow rate will be ym. So that's why we have here ym or my. And then you can also see here that the remaining steam will be 1 minus y. That's why at 0.7, 0.1, and 0.2 it will be the same flow. So that's why 1, 7, and 2 is m 1 minus y, as you can see here in the table. So, and then at 0.3, this y and y minus y will mix all together. That's why at 0.3, it will again become m. So that is how we also determine the flow rate at the different component. Basically, you just look at the different loops in the cycle. It's like a circuit in your electric circuit. So first, we need to determine the temperature and the enthalpy and the entropy at 0.1. Basically, we just use the software. So we can get that already because we have a saturated liquid at 10 kilopascal. 0.2 is process 1 to 2 is isentropic process. So we just copy the entropy and then plug in the value in the software. So we can also get the enthalpy at 0.2. And then at 0.3, it is a saturated liquid. So we can also use the same process as that at 0.1. So we can get also the unknown at point 3. 3 to 4 is a pumping process, as you can see here. So it's an isentropic process. So the entropy will still be the same. And we can use the same process as point 2 to get the temperature and enthalpy at point 4. And then at point 5, we are given with the temperature and pressure. So we can input that in the software and get the entropy and the enthalpy as well. For point 6 and point 7, process 5 to 6 and process 5 to 7 is isentropic process. So therefore, they have the same entropy. So once we have the entropy, we can get the remaining unknown variable. Same also with point 7, it's isentropic process from point 5 because that is just basically the expansion in the turbine. So we can also get the temperature and the enthalpy. So if you can observe, the highest enthalpy in the cycle is 0.5. So now that we have the enthalpies, we can already get the unknown quantities, beginning with the fraction of steam extracted from the turbine, or basically that's Y. So to get Y, what we're going to do is we do an energy balance in the open feed water heater. That's the best first step once you already have the enthalpy. You need to do an energy balance in the feed water heater. So by energy balance, we account for the energy coming in as well as the energy going out of the open feed water heater. So for the energies that entering, so those are M6H6, that's why we have here M6H6, plus M2H2, which is coming from the pump. And then the energy that's leaving the open feed water heater is 0.3, that's why we have M3H3. Then we just substitute the equivalent masses based on the mass flow rate here in this table. So that's why it's very important that the mass flow rate here is already correct. So for M6, that is My, that's why we substitute here My. M2, that is M based on the table. M1 minus Y, that's why we have here M1 minus YH2. M3 is basically M, so we just put here M. So based on that, we can cancel out M because it appears in all terms in the equation, and rearrange this one such that we can get the equation for the value of Y. So now that we have the equation expressing the value of Y, we can substitute already the enthalpies that we already have. So substituting the enthalpies, we can get the fraction of steam extracted from the turbine as 0.2271. So what does it mean? It means that 22.71% of the steam which entered the turbine was extracted for use in the open feed water heater. So now that we have the value of the Y, we can use that to solve for the pump work input. As you can see here, we have two pumps. We can solve them separately or we can solve them as a whole. But for this example, we're going to solve them separately. First, we're going to do energy balance. By energy balance, again, we account for the energy coming in and the energy going out of that particular component. So for the energy that's coming in for pump 1, that is M1H1. And also the energy that you put in the pump to operate the pump. So that's why we have work pump 1. And the energy that's leaving, that is 0.2. That's why we have here M2H2. Also, the mass flow rate of pump 1 is, as you can observe, that is the value 1 minus Y times M. So that's why M1 is equals to M2 because there's no loop here. It's just one circuit if it is a circuit. So that's why the current of steam flowing is just the same. So M1 is equals to M2, and that is equals to M multiplied by 1 minus Y. So if we substitute that in this equation that we have earlier, we will have this, and we can rearrange that to solve for work pump 1. And we can also combine the terms because they have the same mass flow rate. So we already have the equation for the pump work input for pump 1. We can also use the alternative formula using the value of the specific volume at point 1. It will be m multiplied by 1 minus y times specific volume 1 multiplied by the pressure difference across the pump. This is useful if you don't have the software, because by this you can get also the value of the enthalpy. So for the second pump, which is pump 2, we'll use the same process. So we account for the energy entering, which is M3H3, the work of the pump, and the energy leaving, which is M4H4. So we know that the mass flow through pump 2 is M3 and M4, and that they are equal. And if you can also observe, they are equals to value of M based on the table. So we substitute that in this equation that we have earlier, and we rearrange so that we will have this equation. We can also use the alternative formula, M multiplied by specific volume at point 3 multiplied by the pressure difference across pump 2, which is P4 minus P3. Now that we already have the value of pump 1 and pump 2 expression, we just add them together, as you can see here. And if we want to get in terms of kilojoules per kilogram, we need to divide it by m. That's why we will obtain 1 minus y multiplied by h2 minus h1 plus h4 minus h3. Substituting the value of y, which we already solved a while ago, that is 0.2271, and the value of enthalpies found in the table, we can already get the value of the pump work input. So this is already the sum of the pump work input for pump 1 and pump 2. So the pump consumes 16.55 kilojoules of energy per kilogram of steam. So that's for the pump work input. For the turbine work output, we're going to do the same process of energy balance in the turbine. So if you can see, we have energy coming in and energy going out. For the energy that's entering, that is M5H5, and the energy that's leaving are the output, which is also being released by the turbine. So that's why it's in the output side of the equation, plus M6H6 and M7H7. So in the same way, we just substitute the mass flow rate of the turbine. We know that M5 is equals to M, M6 is equals to My, M7 is equals to M multiplied by 1 minus Y. So we just substitute those values in this equation and solve for the work of the turbine. We can also express that in terms of per kilogram. So we just divide the equation with M so that we will obtain this final working equation. So we just substitute the values that we already have so far so that we can get the value of the turbine work output, and that is 1,299 kilojoules per kilogram. So the turbine produces 1,299 kilojoules of energy per kilogram of steam. So since we already have the value of the pump work input and the total output of the turbine, we can also solve the back work ratio. So we just substitute the value of the pump work input and the turbine work output. So the back work ratio is 0.0127 in terms of percentage. We just multiply that value by 100 so that we can get 1.274%. So it means that 1.274% of energy produced by the turbine is consumed by the operation of the pump. For the net work output, we'll just subtract the work input in the pump from the turbine work output. So the net work output is 1,282 kilojoules per kilogram. So the plant produces 1,282 kilojoules of energy per kilogram of steam. For the total heat added, or the heat input in the boiler, we can observe that there's no loop here. We just basically get the difference of the enthalpy across the boiler. So it's H5 minus H4. So the Q in is 2,769 kilojoules per kilogram. So the total heat added by the steam generator is 2,769 kilojoules per kilogram of steam. For the total heat that is rejected, that is Q out, you can see the mass flow rate in the condenser is 1 minus Y. We just multiply that with a change of enthalpy across the condenser. So substituting the value, we can get the total heat rejected. So the condenser rejects 1,487 kilojoules of energy per kilogram of steam. Now that we already have those quantities, we can already get the thermal efficiency. For the thermal efficiency, that is equals to 46.3%. So it means that 46.3% of energy produced by the steam generator will be converted to useful work output. The remaining percentages will be lost in the process. For the heat rate, we just use the same formula, and the heat rate is 7,369 BTU per kilowatt hour. So the amount of heat that is required in the steam generator to produce 1 kilowatt hour is 7,369 BTU. So that is how you solve the different quantities if we have open feed water heater. You can also use the same process. You just have to be careful, especially in the design of the different components. For the next problem, this is the same setup as that of the previous problem that I just solved a while ago. But for this one, we will consider the isentropic efficiency of the turbine as well as the isentropic efficiency of the pump. As you can see, this is already an actual regenerative Rankine cycle with one open feed water heater. The isentropic efficiency of the turbine is 80% and the isentropic efficiency of the pump is 90%. We still have the same operating pressure as well as temperature, and we'll also get the same quantities. We're going to compare the results that we will obtain from this problem to the previous one, which is an ideal regenerative Rankine cycle with one open feed water heater. So first, we're going to draw the schematic diagram as well as the TS diagram. We actually have the same schematic diagram, but for the TS diagram, we're going now to consider the isentropic efficiency of the pumps and the turbine. For the turbine, we're just going to draw the deviation from the inlet of the turbine, which is 0.5, all the way to the outlet, which is at the condenser inlet. So we just draw the diagonal line. As you can see here, at 0.6, the enthalpy will now become 6 actual. 0.7 will now become 7 actual. For the PAM, we're also going to consider the deviation. That's why 0.2 will now become 2A and 0.4 will become 4A. So we need to get the value of 2A, 4A, 6A, and 7A using the relationship for isentropic efficiencies. We'll also get the same value of the enthalpies with the same process that we have for the actual process. So as you can see, we have the same enthalpies from points 1 to 7, but since this is actual, we're going to get the actual values of enthalpies at 0.2, 0.4, 0.6, and 0.7. So using the relationship for the isentropic efficiency of the turbine, so the turbine will, to get the value of 6A, we're going to use H5 minus H6A over H5 minus H6. So we just substitute the value of isentropic efficiency of the turbine, which is 0.8, and also the quantity of H5 and H6 from the table, so that we can get the value of H6A. We can also get the value of H7A using the same process, but the basis is always be 0.5. So substituting the value of the isentropic efficiency of the turbine and the enthalpies H5 and H7, we can get also the value of H7 actual. For the value of H2A, we're going to use the relationship H1 minus H2 over H1 minus H2A. Substituting the value of the isentropic efficiency of the pump, which is 90%, as well as the values of the enthalpies H1 and H2, we can get H2A as 103.14 kilojoules per kilogram. And finally, for H4A, we'll also use the same relationship, but our reference will be H3 and H4. Substituting the value, we can get the value of H4A also. So now that we have the value of H2A, H4A, H6A, and H7A, we're going to put them in the table. As you can see here, we replace the value of 0.2, 0.4, 0.6, and 0.7 with the actual value. And the same process will work. So as you can see, we have the same process. We just substitute the actual value of H2A and H6A to get the value of the steam that is extracted from the turbine. You can find here that the steam that is extracted will become 0.2153 or 21.53%. So this is a decrease from the previous result that we obtained. For the actual pump work input, it's just the same formula, same process. Basically, we just replace the value of H2 with H2A. As well as for H4 with H4A. So substituting the value of H2A and H4A in the equation, we can get the actual work required in the pump. So here, we can see that the pump consumes more power than the ideal, because in the ideal we have 16.55 kilojoules of energy per kilogram of steam. But this time, it increases to 18.41 kilojoules per kilogram. So the result of the irreversibilities in the pump is to increase the work input that will be required for the operation of the pump. For the actual turbine work output, we will have the same process. We just replace H6 with H6A and H7 with H7A. So substituting those values and solving for the actual turbine work output, we will obtain 1046 kilojoules per kilogram. As compared to the ideal process, this is lesser because in the ideal, we produce 1,299 kilojoules of energy per kilogram of steam. So the result of the reversibilities is to reduce the power or the energy that can be produced by the turbine. So the actual back work ratio will also differ. It will now become 1.76%. And that is, if you are going to compare it, it will be greater now as compared to the previous result. For the actual net work output, we just substitute the actual turbine work output and the actual pump work input. So this is also lesser as compared to the result when we have the ideal. Because in the ideal regenerative Rankine cycle with one open feed water heater, we obtain 1,282 kilojoules of energy per kilogram of steam. The actual total heat added will also differ now that we have H4A instead of H4. So the total heat added by the steam generator is 2,767.4 kilojoules per kilogram of steam. It is almost the same as that of the ideal process. For the actual total heat rejected, we'll just substitute H7A instead of H7. So the condenser rejects more energy as compared to the ideal, which is 1,487 kilojoules of energy per kilogram of steam. So as you can see, the result of the reversibility is to produce more waste heat in the condenser. For the actual thermal efficiency, you can also find that the actual thermal efficiency is lesser as that of the ideal, which is 46.3%. This time it is 37.15%, which is a lot lower. And finally, for the actual heat rate, we can find that it has increased because in the ideal it is 7,369 BTU. It means that because of the irreversibility, it will require more heat now in the steam generator to produce 1 kilowatt hour of energy. So this is how you can solve actual regenerative Rankine cycle. So the difference in the process is just to get the value of the actual enthalpies, considering the formula for the isentropic efficiency of the pump and the turbine. The same process will then be applied to all of the quantities that will be needed. So that's it for regenerative Rankine cycle, ideal and actual with one open feed water heater. So in this next problem, we will consider a closed feed water heater. So we are given here with an ideal regenerative Rankine cycle with a closed feed water heater, and we are given with the boiler pressure of 3,000 kilopascal. We're also given with a condenser pressure of 20 kilopascal. Also, the operating pressure of the feed water heater is given, and that is 1,000 kilopascal. It also states here that the closed feed water heater discharges into the condenser after being throttled to condenser pressure. The key term here, throttled, means that this system uses the trap in order to remove the liquid condensate from the closed feed water heater. So instead of pumping the liquid condensate to the boiler, it throttled it to the condenser. So that's why the setup of this one is using the steam trap. So we're going to solve the quantities enumerated from A to I. The schematic diagram representing the given problem is shown here in this slide. So we have a closed feed water heater, and it uses the trap in order to remove the liquid condensate from the closed feed water heater. So we're going to illustrate the movement of steam beginning from point 4, where it enters the turbine at a pressure of 3,000 kilopascal and 350 degrees Celsius. Then at the turbine, we extract a portion of that steam at point 5, and we routed it to the closed feed water heater operating at a pressure of 1,000 kilopascal. The remaining steam expands to point 6, where it will enter the condenser operating at a pressure of 20 kilopascal. You can also find here that the liquid condensate coming from the closed feed water heater leaves it at point 7. So this liquid condensate will be throttled using this throttling device, a trap, to point 8, where it will reach now the condenser inlet, and it enters the condenser and mix with the steam coming from point 6. So they mix here in the condenser, and it leaves as a saturated liquid at point 1. And then it will be compressed by the pump to point 2. And you can also find here that at point 2, it doesn't have to have the same operating pressure of the closed feed water heater, because there's no mixing that happened here in the closed feed water heater, meaning this feed water leaving at point 2 will just pass through using the coil here without mixing. So this is the difference between the operation of the open feed water heater and the closed feed water heater. And that in the closed feed water heater, there's no mixing of the feed water coming from the pump at point 2 with the steam extracted at point 5. So this will just leave at point 3 at the same pressure as that of point 2. And then it enters the boiler, and then the cycle will just continue. So the we have 6 important components here. We have the turbine that produces the work. We have the condenser that rejects the waste heat. The pump that requires work input. We have the boiler that generates the heat. We also have here the closed feed water heater that transfer the heat coming from this extracted steam at point 5 to the feed water entering at point 2. So it basically heats that without mixing. And because of that process, it leaves a liquid condensate at point 7 that has to be removed. So it will be removed by using the steam trap by routing it to the condenser. So the equivalent TS diagram is shown here on the right. So we are going to check the different points if it corresponds with the schematic diagram. So first, it leaves the saturated liquid at point 1 from the condenser. So that's why we have point 1 here. And then it is compressed to point 2. So it's a compression to point 2. So take note that even if it enters the closed feed water heater, there's no mixing that happens here. So we can automatically raise the pressure at point 2 to the boiler pressure. That's why at point 2, the pressure here is not 1 megapascal, but it is 3 megapascal because they don't experience mixing here. So it just passed through so that it will increase its temperature. So point 2 and 3 has the same pressure as well as 3 and 4, and that is 3 megapascal. So point 2, point 3, and point 4 has the same pressure, and that is 3 megapascal. Then we can find here that the steam extracted at point 5, it lives here at point 5. It expands, so from 4 to 5, you can see here. And then it mixes with the, it doesn't mix rather, but it exchanges heat from point 2. And it produces the liquid condensate point 3. So this point 7. This point 7 now is a saturated liquid. So that's why we have here point 7 is saturated liquid, and the pressure is 1 megapascal. So in order to get rid of that liquid condensate, we route it using the steam trap, using a throttling process to point 8, so that it will reach the condenser. So this throttling process is a constant enthalpy process. So that's why the schematic diagram looks like this. So this is as isenthalpic or constant enthalpy process, that is process 7 to 8. Now at point 8, it is now ready to mix with the point 6. So that's why 6 and 8 will mix here in the condenser. And then it will leave as a saturated liquid at point 1, and then the cycle will continue. You can also find here a noticeable increase in the temperature from point 2 to point 3, and that is the result of the exchange of heat between the extracted steam from the turbine that enters the closed feed water heater. So that's why at point 2, it experienced an increase of temperature to point 3, but at the same pressure. So based on the schematic diagram, point 1 and point 7 is saturated liquid. Point 2 and point 3 is subcooled or compressed liquid. Point 4 is a superheated. Point 6 is a mixture, as well as point 8. We also have 3 operating pressures. The pressure of point 2, point 3, and point 4 is 3 megapascal. The pressure of point 7 and point 5 is 1 megapascal. and the pressure of point 1, point 8, and point 6 is 20 kilopascal. So now that we have the schematic diagram and TS diagram, we can use that in determining the enthalpies at the various points in the cycle. So we'll redraw the schematic diagram, and this is the equivalent redrawing. They are just the same. You can redraw the trap using this symbol here, as you can see, process 7 to 8. So since we have 8 points, we create a table, and then we have 8 points, and we plug in the states that we already identified previously, as well as the corresponding pressure and temperature at the various points. Also, for the mass flow rate, if we're going to examine, we have 3 loops here, no? The loops 3 and 4 and 5, and then another loop here, and then another loop here at the bottom. So we're going to determine the mass flow rate through each point. So beginning with at point 1. If we're going to examine, you extract beginning from point 4 rather. So at point 4, we have the mass flow rate at point 4 is the same as the mass flow rate of the steam flowing through the boiler, because there's no loop here in this part of the schematic diagram. So that's why 3 and 4 will have the same mass flow rate, and that is M. So M for point 3 and M also point 4. At 5, we extract Y, so that's why the mass flow rate at point 5 will become My. And then at point 6, the remaining will be 1 minus Y. So that's why at point 6, we have M1 minus Y. So this point 5 here, it will flow through the closed feed water heater without mixing with point 2. So basically, point 5 will just enter the closed feed water heater and will leave at point 7 as the same mass. So point 5, point 7, and point 8 is just the same. They are My. So that's why we have here My for 5, My also for 7, as well as My for 8. And then this My will mix with 6, which is 1 minus Y times M. So if they mix, they will become 1 or 1% or 100% M. So that's why at point 1, the mass flow rate is M. Same also with point 2 is M. And then there's no mixing that happens here in the closed feed water heater. That's why it will leave also as M at point 3. So that is the mass flow rate. So the critical part here in the analysis is the mass flow at the closed feed water heater. You need to know that there's no mixing that happens here. That's why 2 and 3 is just the same pipe, as well as 5 and 7. That's why the mass flow rate through those pipes is just identical. So we are ready to get the enthalpies at the various points, beginning at point 1, since we already have saturated liquid at 20 kilopascal. Process 1 to 2 is isentropic, so we'll just copy the entropy and then get the remaining properties using the software. Point 3 is a subcooled liquid, and we do not know yet, we cannot determine yet the value at point 3. So we're going to determine first at point 4, because point 4 has 2 properties already, and that is 3000 kilopascal pressure and 350 degrees Celsius temperature. And then at point process 4 to 5 is isentropic, so we just copy the entropy, because here you can see an expansion in the turbine from 4 to 5, so we just have the same entropy. So we can also get the properties at point 5. And then at point 7, we can also get the property, since this is saturated liquid. But first, at point 6, we can also get the entropy, because basically 4, 5, and 6 is just isentropic process. They have identical entropy. So we can also get the value of the properties at point 6. So So now that we have the value at 0.6, we are now ready also to get the value at 0.7. So this is saturated liquid at 1000 kilopascal. So we just use that property automatically. And then for 0.8, 0.8 is process 7 to 8 is just isenthalpic process. So that's why we just copy the enthalpy. They have the same enthalpy. So that is throttling process. You can also get the corresponding temperature if we input the value that is already available to us. So if you're going to examine, we do not have the value of the enthalpy at 0.3. But the key to determining the value at 0.3 is that the value of temperature living at 0.3 and 0.7 will be designed such that they will be equal. So that's why the temperature at 0.3 is the same as the temperature of 0.7. If you can also examine, they are both outlet or exit points of the closed feed water heater. So 0.3 and 0.7, the exit points of the closed feed water heater has the same temperature. So we know that the temperature of 0.7 is 179.88. So we just copy that value here at 0.3. Now that we already have the temperature, we can also get the enthalpy. So please remember that the temperature at 0.3 and 0.7 should be designed such that they are identical. They are the points that are exits points of the closed feed water heater. So that's how you determine the different enthalpies at the various points when you have a closed feed water heater. So you can also examine here that we do not use the pumping to get rid of the liquid condensate, but we use the trap. You can also use the same when you design using the closed feed water heater. So no matter how many they are, the same process will work. So the fraction of steam extracted from the turbine, which is the value Y. So the first step is to do energy balance at the closed feed water heater. If you can observe, in our closed feed water heater, the entry points are 0.5 coming from the turbine, the steam coming from the turbine, and at 0.2, which is the feed water coming from the pump and the condenser. And then the exit points are 0.7, the liquid condensate going to the condenser, and 0.3, the feed water going to the boiler. So we do energy balance considering those points. That's why we have this equivalent energy balance. Energy in is equals to energy out. Then we just substitute the value of the mass flow rate that is found here in the table. So for M5, for example, the mass flow rate is My. So that's why we have here My. For M2, we have M, as well as for M3, and then for M7, we have My. So we can cancel out the value of M since it is found in the both sides of the equation. And then we just rearrange and solve for the quantity for the expression that will give us the value of Y. Now that we already have the expression, we just substitute using the value of enthalpies found in the table. So we can get the value of the fraction of steam extracted from the turbine. So there is 24.36% of the steam which entered the turbine that was extracted for use in the closed feed water heater. Now that we already have the value of Y, we can already get the value of pump work input. Using energy balance for the pump here, so energy in is equals to energy out. So we have energy in at 0.1 as well as the pump work input, and then the energy out, which is at 0.2. So rearrange. We know that the mass flow through the pump is just equals to M. So you can also see here that 0.1 and 0.2 has a mass flow rate of M. Substitute that in the equation and then rearrange to solve for work of the pump. In terms of energy per kilogram, we divide the equation with m so that we will have H2 minus H1. So the work of the pump is 3.03 kilojoules per kilogram. An alternative formula is can also be used using the specific volume at 0.1 multiplied by the pressure difference, P2 minus P1. So just in case you do not have the software. So that's how we compute the pump work input. So we only have one pump, so we'll proceed right away to the turbine work output. Using energy balance in the turbine, we can find here that the energy entering is at 0.4 and the rest are leaving at 0.5, 0.6, as well as this green arrow here, which indicates the turbine work output. So the energy balance will look like this. So just substitute the value of the masses. We know that M4 is equals to M, M5 is equals to My, M6 is equals to M multiplied by 1 minus Y. Then we just rearrange so that we can obtain the equation for expression representing the work of the turbine. We just divide everything by M so that we can get this equivalent in terms of enthalpies only. So the work of the turbine is H4 minus Y, H5 minus 1 minus Y multiplied by H6. Substituting the value of H4, H5, and H6 as well as the value of Y that we calculated earlier, we can get the turbine work output as 741. So the turbine produces 741 kilojoules of energy per kilogram of steam. So for the back work ratio, we just substitute the value that we already have, the work of the turbine and the work of the pump. So the back work ratio is, it means that 0.4089% of energy produced by the turbine is consumed by the operation of the pump. The work net or the net work output can also be computed already. Just substitute the value, we can get that the plant produces 738 kilojoules of energy per kilogram of steam. Okay, for the total heat input or total heat added, we're going to pay our attention to the boiler. Using energy balance in the boiler, we have energy incoming to the boiler are M3H3 as well as the heat added because of the source of heat, and then we have the outlet at 0.4. So the energy balance is like this. So substituting the value of these quantities in terms of the mass flow rate of the steam through the boiler, we can find that we can cancel out the value of M and then rearrange so that we can get the value of Qin. So our Qin is just the difference of the enthalpies across the boiler. Substituting the value of enthalpies, we can get Qin as 2353. So the total heat added by the steam generator is 2353 kilojoules per kilogram of steam. For the total heat that is rejected, we're going to give our attention to the condenser. Using energy balance in the condenser, energy in is equal to energy out. We can see here that the incoming are 0.6 and 0.8, and the outgoing are Q out, which is the energy rejected here indicated by this red arrow, as well as the energy leaving here at 0.1. That's why we have here M1H1. Substituting the value of the mass flow through the condenser, we M6, M8, as well as M1, we can find this equation instead. And we can also rearrange to get Q out. And in terms of small Q out or per kilogram, we will have this equivalent expression. So substituting the value of enthalpies as well as the value of Y, we can get Q out as 1,615 kilojoules per kilogram. So the condenser rejects 1,615 kilojoules of energy per kilogram of steam. So now we can get the thermal efficiency. We just substitute the value of work net and the heat input that we already have. So the thermal efficiency is 31.36%. It means that 31.36% of energy produced by the steam generator is converted to useful work output. And You can also get the heat rate by using the value of the thermal efficiency. So this means that the amount of heat required in the steam generator to produce 1 kilowatt hour is 10,880 BTU. So that's how you solve for a regenerative Rankine cycle using a closed feed water heater. You have to be very careful when doing the energy analysis as well as doing the TS and schematic diagram, because it will really help in solving the different quantities. Once your schematic diagram or TS diagram is incorrect, that it will also follow that the solution would be incorrect. And then finally, we have another problem here, wherein we have an ideal steam regenerative Rankine cycle with 2 feed water heaters. We have 1 closed and 1 open. The operating pressures are 10 megapascal for the boiler. We have 10 kilopascal in the condenser. 1.2 megapascal for the closed feed water heater and 0.6 megapascal for the open feed water heater. It's also stated here that the feed water is heated to the condensation temperature of the extracted steam in the closed feed water heater. And also, the extracted steam leaves the closed feed water heater as saturated liquid, which is subsequently throttled to the open feed water heater. So it means that the liquid condensate that is produced in the closed feed water heater is throttled to the open feed water heater. So it's not throttled to the condenser, but it's throttled to the open feed water heater. And there's a throttling process, so it means that it uses the trap also. And in this problem, we are given with a net power output of 400 megawatt, and we're going to solve the different quantities that you can find here in the slideshow. So for the equivalent schematic diagram, this is how it would look like. So you can find here the 4 operating pressure, the 10 megapascal. The 10 megapascal for the boiler pressure, you can also find that here in the TS diagram. The 1.2 megapascal for the closed feed water heater, we have here 1.2 megapascal. We have 0.6 megapascal for the open feed water heater, that's why we have here 0.6 megapascal. And the condenser pressure of 10 kilopascal, that's why we have here 10 kilopascal at the lowest constant pressure line. And we have 1 closed and 1 open feed water heater. And as you can see here, there is a portion of steam, which is Y, extracted and is brought to the closed feed water heater without mixing, because this is a closed feed water heater. So it will just exit the closed feed water heater at 0.6 as a saturated liquid. That's why 0.6 here is a saturated liquid at the pressure of 1.2 megapascal, which is the pressure of the closed feed water heater. And then it's stated in the problem that this liquid condensate leaving this closed feed water heater is throttled. So this is the throttling process that was mentioned, this process 6 to 7. It's throttled to the open feed water heater. So unlike the previous problem wherein it was throttled to the condenser, here it's throttled to the open feed water heater. So that's why we can find here this isenthalpic process 6 to 7. So it's not 6 to this lowest pressure here, but at the pressure of the open feed water heater. So take note that in the closed feed water heater, this tube representing 9 to 6 and this tube representing 4 to 5 does not mix. So there's no mixing happens here. Whereas in the open feed water heater, all of this fluid entering will eventually mix, and it will exit at 0.3 as a saturated liquid. That's why we have here 0.3 is saturated liquid. So 0.3 is just a mixture of 0.2, 0.7, and 0.10. So this 0.2, this 0.7, and 0.10 has the same pressure in order for them to mix. So they have to be at the same pressure. So 0.3, 0.10, 0.7 has the same pressure. Also, when it comes to the steam extracted, so again at 0.9 we extract Y, and then at 0.10 we extract Z. So that's why the remaining steam entering the condenser will be the total minus Y minus Z. So if we're going to check the TS diagram, we can find that at the condenser, the pressure of 0.11 and 0.1 is the same. Also, at the open feed water heater, the pressure at 0.3, 0.7, 0.2, and 0.10, they are the same. So we have 0.2, 0.3, 0.7, 0.10, they are 0.6 megapascal. And also at the closed feed water heater, since 9 will not mix with 4, it will have the same pressure as 0.6. That's why 9 and 6 has the same pressure. So 6 and 9 has the same pressure. And then this saturated liquid leaving at 0.3 will just pass through the closed feed water heater without mixing. So it means that 0.4 will have the same pressure at 0.5 and 0.8. So that's why we have 0.4, 0.5, and 0.8 has the same pressure, and that is 10 megapascal. Also, another property in the design is that the temperatures leaving the closed feed water heater has the same temperature. That's why T5 and T6 will be the same. You can also find here that they are in a horizontal level. Though they are not connected in the same piping, they will be designed in such a way that 0.6 and 0.5 has the same temperature. So that's the property of a closed feed water heater. So that is the schematic diagram and the equivalent TS diagram for when we have a closed feed water heater combined with an open feed water heater and using a steam trap to handle a liquid condensate leaving the closed feed water heater. Now that we already have the schematic diagram and the TS diagram, we are now ready to get the enthalpies at the various points in the cycle. So as you can see, we have 11 points, and we also noted there the different states of the different points, the pressures at the different points, as well as the temperature that is given. We can also analyze the mass flow rate flowing through each of the components by looking at the different loops in this cycle. The equivalent mass flow rate are shown here in this column. So first, we're going to get the enthalpy at point 1 using the saturated liquid at 10 kilopascal. Then we have process 1 to 2 is compression by the pump, so that's isentropic process. So we can also get the properties at point 2. And then we'll also get the property at point 3, since point 3 is saturated liquid. So when it leaves the open feed water heater, it will become saturated liquid. So that's why we have this value here. Then we can also get the entropy at point 4, since you can see here that process 3 to 4 is pumping, so it's isentropic process. So we can get the value of enthalpy and temperature at point 4. Then at point 5, we cannot get yet the value, since as you can see here, we have a subcooled liquid and we only have one known property. In order to get the value of 0.5, we have to know first the temperature at 0.6, because 0.6 and 0.5 has the same temperature. So we will get first 0.6. So 0.6 is saturated liquid, so we can automatically get the unknown values. And now that we have the value of temperature at 0.6, since they are the same as 0.5, they are the exit points of this closed feed water heater. We'll just copy this one to 0.5, and then we can also get the remaining properties. Then at point 7, so if we're going to check at point 6 to 7, this is actually a throttling process. This means that they have the same enthalpy. So we just copy the enthalpy of 0.6 to 0.7. Then point 0.8, we have two quantities, so we can get all of the values automatically. And then for point 9, 10, and 11, this is isentropic process. This is expansion in the turbine. So we just copy the entropy from 0.8. And then since we already have two known quantities, we can also get the remaining quantities. So that's how you can get the various enthalpies at the points of this cycle. Now that we have the enthalpy, we can get the fraction of steam extracted from the turbine. First, the value of Y. So we're going to get value of y by doing energy balance in the closed feed water heater. So energy entering is equal to energy leaving the closed feed water heater. So entering are 0.4 as well as 0.9. Leaving are 0.6 as well as 0.5. So substituting the value of the mass flow rate, and then since we have the same quantities of m at both sides, we can delete that, and then we can rearrange for y. So as you can see, we already have the expression for the steam extracted for the closed feed water heater. Substituting the value of the enthalpies, we can get the value of y as 0.0541, or 5.41% of the steam which entered the turbine at point 8 was extracted for use in the closed feed water heater. So this is the steam flowing at point y is 5.41% of the total that flows here at point 8. And as you can see, we still have another extraction here at point 10, which is z. So that's why we need to get also that fraction of steam extracted for the open feed water heater. So we're going to do energy balance at the open feed water heater. Energy entering are 0.10, 0.7, and 0.2. The one that is leaving is 0.3. So that's why we have here 0.3. Substituting the mass flow rate, and then deleting the value of m, and then substituting the value. Since we have 2z here, we can actually use shift solve, or you can also rearrange so that you can get the equation for z, whichever is convenient to you. So for me, I'll just use shift solve, and then I got z as 0.1694. So 16.94% of the steam which entered the turbine at point 8 was extracted for use in the open feed water heater, and it is extracted at point 10 and routed to the open feed water heater. So now that we already have the value of the extraction of steam at point 9 and point 10, the y and z values, we can already get the other quantities. First, the pump work input. So for the pump work input, unlike what we did previously, we can also do an energy balance for the combined pump. So we have two pumps here, pump 1 and pump 2. So using energy balance, combining point 1 and pump 2, energy entering and energy leaving the pumps, the entering are point 1, which enters here at pump 1, and also point 3, which enters here at point for pump 2. That's why we have here M1H1 plus M3H3. We also have the total pump work input. So this is already the sum of pump 1 and pump 2. The energy leaving are at point 2 as well as point 4. So as you can see, we already combined the process instead of having individual energy balance for pump 1 and pump 2. So rearranging, we can get the equation for the work of the pump, but we need to substitute the value of the mass flow rate through the pump. We know that M1 is equals to M2, and that is equals to 1 minus y minus z multiplied by m. Also M3 is equals to M4, and that is equals to 1 minus y multiplied by m. Substituting those quantities, we can get the work of the pump in terms of per kilogram. Substituting the value of y and z as well as the values of enthalpies, we can get the pump work input as 10.21 kilojoules per kilogram. So this represents already the total pump work input. So now that we have the pump work input, we can already solve the turbine work output also. Using energy balance in the turbine, energy in is equal to energy out. Then substituting the value of the mass flow rate and rearranging for the work of the turbine, and noting the mass flow rate through the various points connected to the turbine. M8 is equal to M, M9 is equal to My, M10 is equal to Mz, M11 is equal to M multiplied by 1 minus y minus z. So the work of the turbine is expressed in the equation that you can see. Substituting the value of those enthalpies and the values of y and z, we can get the turbine work output as 1,289 kilojoules per kilogram. So since we have the pump work input as well as the turbine work output, we can already get the back work ratio. So substituting the value, we can get the back work ratio as 0.7921%. Also, the network output can already be determined using the value of the work of the turbine and the work of the pump. So the network output is 1,279 kilojoules per kilogram. Then for the mass flow rate of steam through the boiler, this is one of the unknown in this problem. We can use the formula work net is equal to mass flow rate multiplied by work net. So this M represents this M that you can also find here in the table for the mass flow rate through each of the components. So from the given, we know that the power output of this power plant is 400 megawatt, and that is equals to 400,000 kilowatt, or 400,000 kilojoules per kilogram. We know that the work net also is 1,279 kilojoules per kilogram. So we can already solve the mass flow rate of steam through the boiler, and that is 313 kilogram per second. So take note that this mass flow rate represents the mass flow rate of steam flowing through the boiler. So it is different when it already flows here at 0.9, because it's already we already extract a value here as well as here at 0.10 and also at 0.11. You can get the actual value of the flow rates at those various components by using this formula here for the mass flow rate. Basically, you just multiply the factor, the extraction factors to this value of M. So the boiler produces 313 kilogram of steam per second. So that's a huge amount of steam per second. We also have an alternative solution to get the mass flow rate of steam through the boiler without doing the computation of the work of the turbine and work of the pump. This is by doing an energy balance in the entire power plant. By saying energy balance in the entire power plant, we just consider the four major components: the boiler, the pump, the condenser, and the turbine. So we know that the energy entering in the entire power plant are the boiler as well as the pump. The energy out are the condenser as well as the turbine. So rearranging that, we know that QB minus QC will then be equals to work P minus work pump. And we know that this quantity is known also as the work net. So work net is just equals to work turbine minus work pump, or Q boiler minus Q condenser. So the work or the Q of the boiler is just equals to mass multiplied by H8 minus H5, or the difference of enthalpies across the boiler multiplied by the mass flow rate through the boiler. And then for the condenser, it's equals to the enthalpy difference in the condenser, which is H11 minus H1, as well as multiplied by the mass flow rate to the condenser. So in this way, we can rearrange that to get the value of the mass flow rate. Since we already have the value of work net and these values here, we can already get the mass flow rate. So the mass flow rate using this alternative solution is 314 kilogram per second. So there is a difference of 1, maybe because of the rounding off of the values that we have previously. So it is easier to get the mass flow rate using this process as compared to the previous one, because in that process you need to get the value of the work turbine, work pump, which requires a lot of energy balance. So for the total heat input, that is the heat input in the boiler. So just substitute the change of enthalpy across the boiler. So we get 2,823 kilojoules per kilogram. For the heat rejected at the condenser, we just multiply the mass flow rate to the change of enthalpy. So the heat rejected in the condenser is 1,549 kilojoules per kilogram. So we have the thermal efficiency as work net over Qn, and that's equals to 45.31%. So you can see here that there is 45.31% energy produced by the steam generator that is converted to useful work output. And finally, for the heat rate, we just substitute the value of the thermal efficiency. So the heat rate is 7,530 BTU per kilowatt hour. So that's how you solve if there is a combination of closed and open feed water heater. You really have to analyze the given problem whether it uses a trap, what kind of arrangement is being described based on the sentences in the given problem. So there's no one solution for problems involving regenerative Rankine cycle, unlike the other cycles that we tackled previously. Here we really have to analyze which part is connected to which part, what mass flow rate flows to each of the components, and we need to do a lot of energy balance in order to get those unknown quantities. So I hope that you learned something from this. So see you in our next lesson.